Hey there, welcome to Calculus, and this is our first video lecture of our summer course, and we're going to be talking about material from section 2.1. It's called the tangent line and the velocity problems. So it's two, at first glance, very different problems. Finding tangent lines is kind of a problem from geometry, analytic geometry about curves in the plane, and finding the velocity or instantaneous velocity of an object in motion is kind of a problem from physics. And when you first start looking at these two things, they seem like they're from totally different worlds. And we're going to try to sew them together with one mathematical idea that will in turn be the content of what we're going to study in chapter 2. Okay, so let's get going here. I want to tell you what do I mean by a tangent line. So let me click ahead a couple slides here. I've drawn a curve in the plane there. We don't have to worry about what its formula is, but it's drawn in blue. It's the graph of some function. I'm just calling it y equals f of x. And I picked one point on the curve. You can see it's drawn as a blue dot there. And then I've drawn a red line through that point. And you know that it takes 2 points to determine a line. So if you're only interested in that red line going through this one and only one point, there's infinitely many lines in the plane that go through that point. I can kind of slide this thing up there. I called my slider M, because what I'm doing is I'm just changing the slopes of those lines. They're all going through the same point, but I'm just changing the slope. Here it looks like I just about made it to slope equals 0. It's a horizontal line, and now the slopes are positive. So there's infinitely many lines through that point on that curve. Every point in the plane has infinitely many lines. But one of those lines, I'm just going to use this picture to define this notion, is so-called tangent to the curve. So what do I mean by tangent? By tangent, I mean it intersects the curve at that point just once. Well, I mean, a line is going to cross a curve. It's intersecting it over here as well. But when I'm thinking about tangent, I want it to intersect just locally at one point. But it's got to have the sort of right direction as well. So these lines that we're looking at right now, they're all intersecting locally at one point, but they don't have the same direction, quote unquote, as the curve. If we get to a line that looks like its slope is something about right there, that's kind of what I mean by tangent. That line is intersecting the curve locally. I don't mind if there are other intersection points far away, but near the point that I'm looking at, the line is touching the curve once, and it's got kind of the same direction. What do I mean by the same direction? Let's zoom in. I'm going to click ahead a couple of slides here, and we're going to be looking at this same picture, but just zoomed in around that point. So here we are kind of in close, and I've got that same line drawn there, and it's tangent in the following sense. If I perturb the slope of this line at all, so right now the red line is touching the blue curve only at that blue dot. If I make that slope even slightly bigger, I introduce a second intersection point. By making the slope bigger, the intersection point ended up over here on the right. If I made the slope slightly smaller, I introduce a second intersection point. So you can kind of imagine I'm trying to find like, well, where is exactly the right slope of that red line that it touches once? You know, imagine that the blue curve is actually built up like it's a little wall coming perpendicular out of your screen, and you're just pushing this red line up against the wall so that it's touching at that point. It would be tangent. And I want to know that slope. Okay, so I can scroll a little bit here and let you still look at the picture while I pose. What is this tangent line problem? Well, the tangent line problem is given some function, y equals f of x. It's a given. And then you give me some point on it, a comma f of a. I just drew the point as a blue dot. The question is, well, what's the slope of the line that's tangent to that graph? Okay, why is that an interesting problem? Why is the tangent line problem a challenging problem? Well, it's challenging because we're trying to find the slope of a line, but we only know one point on it, right? The old saying is that it takes 2 points to determine a straight line. That's true. If you think about how you calculated slope in pre-calculus, you took the change in y over the change in x. What were those changes calculated from? From 2 points. But we only have 1 point. So that's why this tangent line problem is kind of interesting and challenging, is I'm trying to find the slope of a line, and in terms of coordinates on the line, I only have one of them. Of course, I also know that the line's supposed to be tangent, and that's what we have to take advantage of in order to be able to do this. All right, so what we're going to do, this is an idea, we're going to give ourselves a second point on the curve. That is, we're going to look at a family of lines that are all called secant lines. Let me show you what I mean. So I've gone back to our picture here. I've got the usual point, the same point that we've drawn that red line through. It's never going to move. But over here, I've drawn a second point on the curve. If you pick 2 points on a curve, this is just a definition, 2 points on a curve, the line through them is called a secant line to that curve, okay? So a tangent line touches the curve in exactly 1 point with the same direction. A secant line is a line through 2 points on a curve. And what I can do in this little animation here is I can change the slope of that red line. That is, I'm changing the location of this second point, okay? And as you'll see, if I drag that second point closer to the first one, the one that's fixed, then those secant slopes change. These secant slopes are something that we can compute, right? We have 2 points. We can take the change in y over the change in x. We can compute those slopes. So the idea is, well, the closer and closer this second point gets to our initial point, the closer and closer those secant slopes seem to be getting to the slope of the line that I want. When these 2 points coincide, we can't calculate the slope. Let's see if my software will complain if I try to put those dots right on top of each other. It is complaining. Oh, it's complaining loudly. It's telling me that I've divided by 0 because everywhere I was computing a slope, you didn't see it in the picture, and I just made the change in x 0. So the program is not happy. As long as those 2 points aren't in the same location, then it can happily compute the slope of the red line, and that's how I'm plotting the red line. But if the 2 points coincide, then the computer complains. I exactly want to know what the slope of that line is when those 2 points coincide. So again, this is kind of getting more and more interesting. It's like a mystery. All right, so that's what the tangent line problem is. The tangent line problem is, how do we find the slope of a line to a curve that's to a line that's tangent to a curve at a given point? And what we're going to do is flip back to a whiteboard slide that I can do some writing on, and we're going to write down an expression that computes the slope of these secant lines as a function of where the second point is. Okay, and then we're going to just see if we can't try to understand how that secant slope function is behaving. So now I'm gonna switch my screen share. There's always going to be a little bit of a delay here. You'll see as we make these videos in this course that my purpose is to try to talk and teach mainly to you guys, not to make super high quality polished YouTube videos, but I do promise you that I'm trying to make the best videos that I can. So here we're back at a whiteboard, and you can see I've got that same picture, and I'm actually revealing now what the formula for our function was. That's a cubic function, f of x, and its formula is given by x cubed minus x squared minus 2x. Okay, and the point that I'm looking at, I chose the value of a to be 1. So I'm looking at the point 1 comma f of 1. And maybe you can pause this video for a second before I do it. What is f of 1? I need to know the second coordinate there. So how do you evaluate a function? Well, you replace the input with the specified input variable. So in this case, I would have to take 1 cubed, subtract 1 squared, and then minus 2 times 1. So 1 minus 1 minus 2 is negative 1. So our point that we're looking at for tangency here is the point, excuse me, here's our first chance to see that I won't edit these videos. 1 minus 1 minus 2 is negative 2. Negative 1, so hopefully you correctly computed that. So we're looking at the point 1 comma minus 2. That's where I'm trying to find the tangency. The second point up here, I'm going to leave it as a variable. I'm going to just call its input x, and well, its output, whatever x is, it's x cubed minus x squared minus 2x. All right, so now I'm in a position where I've got 2 points. I've got the coordinates 1 comma minus 2. The other one, it's in terms of a variable, but its first coordinate is x. Its second coordinate is that cubic polynomial. We can compute that secant slope. I'm going to slide the screen a little bit to give myself enough room to write here, and let's do it. So what is the secant slope? Remember, secant just means line that has 2 points on a graph of a function. So it's that red line is the secant line I'm looking at. And well, I'm going to compute the slope like you usually do. I'm going to take the change in y over the change in x. Maybe you use the same kind of notation I do, the change in y over change in x, using that Greek symbol capital delta for the change in. Well, and what are my y coordinates? I'm going to do them in this order. My first y coordinate that I'm going to use is the one x cubed minus x squared minus 2x. So I'm going to take that expression, x cubed minus x squared minus 2x, and then I'm going to subtract from it my second y coordinate. Well, what is the second y coordinate? That's this minus 2. So I'm subtracting a -2. I'll write it like that so the notes are easier to follow. Then I have to take the change in the input coordinates. Well, the corresponding change in the input coordinates is x minus 1. So if I try to simplify that just a teeny little bit, there's not much I can do. I'll just try to write it in nicer handwriting. X cubed minus x squared minus 2x. Subtracting -2 is like adding 2. So what is this expression that we've written down? It tells us the slope of that red line given an x value, given the second coordinate on it. All right. The only x value that I can't plug into this expression is the one and only x value that I want to know. I want to know what's the slope of that line when x becomes 1. But now you can kind of see why my computer program was complaining when x became 1, because I was dividing by x minus 1, and that's dividing by 0, which is mathematically not allowed. Division by 0 is not defined. But what we can do is we can choose any value of x except x equals 1 and compute that slope. Here, let's start off with one. I'm going to choose x equal 2 to keep the arithmetic light. So if I let x equal 2, I can ask myself, well, what's the secant slope? I've got this expression for it here, so I can just replace x with 2 and compute it out. So 2, I'm gonna do the arithmetic as I speak here, so that I don't run out of room. So 2 cubed is 8, 2 squared is 4, 2 times 2 is also 4, and you have to add 2, and then, well, in the denominator, 2 minus 1 is 1. And let me go slower here so I don't blow it. 8 minus 4 plus 2 is 2. Okay, so what does that mean? That means that when we chose this second point to be at x equals 2, I can draw it in the picture here. You can imagine in your mind the corresponding red line. That line has slope 2. The slope of the line through those 2 points has slope 2. All right. And then if you wanted to know some other x value, if you wanted to choose, say, x equals, I don't know, 1.1, you could choose x equals 1.1 and go through a similar computation. What would we have to do? We'd have to say, well, the secant slope is, this time I'm just going to write it out, and then you can pause the video and do the calculation, but you'd have to take that 1.1 and cube it. It's probably something you want to do on a calculator for speed. Then you have to take 1.1 and square it. You have to subtract 2 times 1.1 and add 2. And divide all of that by 1.1 minus 1. That'll give you some new secant slope. And based on the pictures that we were looking at, this new secant slope is a better approximation to the tangent slope that we want. Because the idea is the closer we choose x to the point that we are trying to look at, we're trying to look at x equals 1, the better the secant slope will approximate the tangent slope, or at least that's what the picture looked like. So pause the video and compute this out. I'm just going to write the answer right now, but this is a chance to see if you can follow the order of operations and get the correct value. But if you compute this thing out, say to 2 decimal place accuracy anyway, you should get something like -0.79. All right, so if we take the x value to be 1.1, you can get -0.179. So here's the idea. Let's let x get closer and closer to x equals 1 and compute the secant slope every time. Every time, I mean for every value of x. If those secant slopes approach something, then we can use that something to take a guess for our tangent slope. Okay? So to keep this video short, I'm going to show you a couple of tables, but I hope that you're going to kind of take a calculator out and make sure that you can reproduce the values in these tables. We've done just 2 of them up here. We did x equals 2 and x equals 1.1. So let me sort of scroll the screen a little bit so you can get a view of these tables. So I've got 2 of them here. Let's start on the one on the left. I'm writing my x values in the left-hand column and then the corresponding secant slopes in the right-hand column. These first 2 rows are what we've done above by hand. When x was 2, the slope was 2. When x was 1.1, I hope you stopped the video and computed with me that the slope was -0.79. And then what am I doing? I'm just kind of letting x get closer to 1 in sort of a systematic way. I'm just looking in fancy language at an order of magnitude closer every time. So instead of 1 plus a tenth, 1 plus a hundredth, a thousandth, 10,000th, and so on. This line down here just means that the way the computer program I used to format this table, the number was so close to 1, it didn't reproduce all the zeros. But you can think of it, it's 1.50000001. All right, and over here in the right-hand column, the computer program computed the slope for every one of those things. And I'm looking at a pattern. Those numbers in the right-hand column look like they're getting closer to something. What's this table over here on the left? It's the same idea, no new idea. I'm just choosing values of x that are getting closer to 1 from the other side, quote unquote. All of the numbers in my first table are slightly bigger than 1. All of these numbers are slightly less than 1. But again, looking at the corresponding output columns in both tables, the closer and closer I get to the value 1, either from values that are slightly more than it or values that are slightly less than it, it looks like the secant slopes are approaching the same value. Can you say what that value is based on this? Maybe stop the video. I'm talking fast. I always will talk fast in these videos to try to keep them short. But if you can look at these two tables and say, well, it looks like the closer and closer x gets to 1, the closer and closer those secant slopes gets to, well, -1. So that's my tangent slope estimate. I'm thinking that the slope of the line that's tangent to that cubic polynomial at when x is equal to 1, it looks like the tangent slope is -1. All right. How could we kind of confirm that that guess looks okay? Well, we could write down the equation of the tangent line. How do you write down the equation of a tangent line? My favorite way to find the equation of a line, if I'm given a point on the line and given the slope of that line, is to use this so-called point slope formula. Yeah, if you look up in algebra books or wherever you saw this stuff, people usually call this the point slope formula. Point slope form of a line. And it's nice because you use it exactly when you have those two pieces of information, when you have a point and you have the slope. That's precisely what we have here, right? We said that the point that we're talking about is at 1 comma -2, and we just took a guess for the slope to be -1. So if we kind of run that through here, we take y take away -2 is -1 times x minus 1. And if we simplify that a little bit, what will we get? We'd get +1, take away 2, so it's going to end up just being y equals minus x minus 1. You can stop the video and kind of confirm that. Make sure I didn't make a mistake. Okay, so this is my guess for the tangent line. This should be the tangent line to that curve. So if I graphed our curve, our cubic polynomial, and this tangent line on the same screen, then I can kind of confirm. If it doesn't look tangent, then I probably made some mistake. If it does look tangent, then this guess is probably accurate. Let me switch over to Desmos. I'm going to try to use Desmos all the time here with you guys in this class. So let me switch over to the Desmos screen that I've got ready. I've got it already typed in, so I don't have to type in front of you guys. So here you're looking at it. I've typed the tangent line in first. It's in the same color that it was on my slides, minus x minus 1. We just derived it. Here's our cubic polynomial, x cubed minus x squared minus 2x. And looking at this picture over here, it looks to me like that is the right slope. It looks like that line is touching the curve at the point 1 comma -2. And locally, again, I don't care if it touches it far away. That's kind of more of a question about how the curve bends or doesn't bend. But locally, in the sense that if we zoom in here around the point x equals 1, that we should see that that's the only point that the line is touching the curve. So I can kind of zoom in with Desmos just by hitting this plus button a couple of times if you like. So you can kind of look at the scale to see how close we're getting. But the closer and closer we get, the line and the curve are kind of becoming indistinguishable. This is kind of going to be a topic that we're going to study in chapter 3 called differentiability. But in this picture, I can see that that slope looks like it's perfect. That at the point 1 comma -2, that red line is touching the blue curve, but nowhere else. All right, so that is the tangent line problem. Okay, so let me switch back. This section was called the tangent line problem and the velocity problem. So let me switch back and try to give you a sense of what I mean by the velocity problem. Should be back live here in a second. There we go. So the velocity problem. Well, I mean, very briefly, simply stated, it's find the instantaneous velocity of an object in motion. The instantaneous velocity in the sense of that its velocity, its rate of change in position, but not over an interval of time, but over just an instant of time. So here I can give you kind of an example. You compute average velocities, not instantaneous velocities, by taking the change in position over the change in time, right? Because distance is equal to rate times time. Well, that means rate is distance over time. So here, just to put that in kind of a concrete example, suppose that you take some road trip, you drive your car, and you drive 210 miles in exactly 3 hours, just for simplicity of this example. All right. So your average velocity is, well, your change in position was 210 miles. Your change in time was 3 hours. And so your average velocity is 210 divided by 3, or 70 miles per hour. That doesn't mean you were going 70 miles per hour the entire trip, right? It just means that on average, you were going 70 miles an hour. So this velocity problem I'm talking about, it's more about instantaneous velocity. So if I asked you like, hey, 1 hour into the trip, exactly 1 hour into the trip, what did your speedometer in your car read? Your speedometer is telling you what your instantaneous velocity is. Yeah. So you can't recover the instantaneous velocity only from the average. I don't know, 1 hour into the trip, maybe you were going 80 miles an hour, maybe you were going 60 miles an hour. I don't have any way of saying that from this average. But that's what a velocity problem is I'd like to be able to compute the instantaneous velocity of an object in motion, not just its average velocity. All right. So to illustrate this, I'm going to take an example from the book. It has better graphics than what I could produce. And then it's also there for you to refer to. So it's going to be example 3. I took this from page 80 in your textbook. If you want to just check it out there as we're going along. I tried to take this nice graphic because I didn't know this CN Tower in Toronto. I've never been to Toronto, Canada. I'd like to go there sometime. But evidently it was the tallest freestanding building in the world for 32 years. I don't know when that 32-year period began or ended, but maybe when I'm done making this video, I'll do some Google searching. Okay, but so here's the example. We drop a ball from the upper observation deck of the CN Tower, which is 450 meters above the ground. It's quite a distance. And the question is, well, what is the velocity of the ball 5 seconds after we dropped it? Okay, so that's the manifestation of the velocity problem. Something is falling through the air, its position is changing, and we're asking what its velocity is exactly 5 seconds after we dropped it. So it's an amazing fact that more than 400 years ago, Galileo, via experiments, was able to deduce that the distance traveled by a falling object is proportional to the square of the amount of time that it falls. And through further experiments, and I'm ignoring air resistance here, different objects will fall at different rates depending on their air resistance, but making some of these simplifications here on Earth, that the constant of proportionality is approximately 4.9. Here I'm measuring distance in meters, time in seconds, okay? So we're gonna use this model of Galileo that if you drop an object, ignoring air resistance, so think of the object as something that wouldn't be much affected by air resistance, like a heavy ball, a baseball, a basketball, or not a basketball, a bowling ball, something whose air resistance would essentially be negligible. Then the distance in meters that it travels in t seconds in free fall is 4.9 t squared seconds, or t squared meters, excuse me. So how are we going to use that information to calculate the velocity of this ball 5 seconds after we drop it? Right? Because what can this thing tell me? Like if I plug in 5 into this formula, if I calculate S of 5, 4.9 times 5 squared, well, that tells me how far it's fallen in 5 seconds, right? So if I took that number and divided it by 5, if I took, say, S of t or S of 5 and divided it by 5, that would give me the average velocity. But I want to know its instantaneous velocity. So here's kind of an idea. We'll go back to the text. Here we're kind of starting to see maybe why we're talking about these two problems in the same lecture, because the difficulty here, the author says, in finding this velocity is that we don't have an interval of time over which we can average, right? If I want to know the velocity at 5 seconds, I don't have a time interval that I can divide by. I can compute average velocities, but how do I compute this instantaneous velocity? Well, the idea is that we'll just compute average velocities and we'll do it over smaller and smaller intervals of time. So I'm going to add to the text here this change in position. If you gave me a time value, say t seconds, and I plugged that into this function, that tells me how far the ball has fallen in t seconds. If I subtracted from that the function's value at 5, how far the ball fell in 5 seconds, then this quantity would be the change in position, right? How far you've gone after t seconds minus how far you've gone after 5 seconds is how far you went in the interval from 5 to t seconds. And if I divide that by the length of that time interval, that is, I divide that by t minus 5, my change in time, then I would get the average velocity. And here in the numerator, the units, everything is measured in meters. The distance of two things measured in meters is in meters. In the denominator, we're measuring things in seconds. So the units on this average velocity are meters per second. Yeah. So here, the author has taken the time interval to be from 5 seconds to just a tenth of a second later. So this S of 5.1, that's how far the ball fell in 5.1 seconds. S of 5 is how far it fell in 5 seconds. So this numerator, this difference, is how far did the ball fall in the tenth of a second from 5 to 5.1. So the author has kind of simplified this. 5.1 minus 5 is just 0.1. So the denominator is 0.1. You can stop the video here. Remember that S of t is just 4.9 times t squared. So this 5.1, the input here in S is just getting squared. The 5 is getting squared. Stop the video, take out your calculator, and make sure the order of operations are going swell for you. You should reproduce this quantity, 49.49 meters per second. Right? That actually should be a reasonable estimate for how fast this ball is traveling in 5 seconds because we averaged it over a pretty small time interval. So I'm just going to scroll here, and I hope you'll take out a calculator and reproduce every one of the rows in this table, actually, because what is the author doing? Here's the row that we just analyzed above. Over the tenth of a second, it's following, so the interval from 5 to 5.1 seconds, the average was 49. Earlier in the table, the author averaged over a full second from 5 to 6 seconds. Yeah, so it's not as good of an estimate because that time interval is longer. Here, averaging over a 500th of a second. So it's sort of half as long as the previous interval. Over 100th of a second, over 1,000th of a second. Yeah, so smaller and smaller time intervals. Each time we can compute the average and look again what's happening. These numbers are not just sort of random. They're not flying all over the place. They're getting closer to something. They're getting closer to something. So based on this table, here's another dramatic pause you can make in the video. Based on that table, what would you say if you asked someone were asking you, well, what is this ball's velocity exactly when t is 5 seconds? The smaller and smaller time interval we averaged over, so the closer and closer that this second point got to 5, then the closer and closer these average velocities are getting to what number? It looks like it's 49 meters per second. So my answer to the question, how fast is this ball falling at exactly when t is equal to 5? What's its speedometer reading, if you like? I'm going to answer 49 meters per second, which is quite quick. 49 meters, you can think of if you've ever been around a track or a US football field, that's about half the length of it. So half the length of a 100-meter dash in 1 second. It's moving quite quickly, this falling ball. Cool. Well, that's kind of, I mean, I want to recap these ideas here. I do want to take just 1 second to flip over and give you some technological tools. This is an online course and you'll have some technology in front of you. So I want to do this as much as possible. Creating these tables, if you stopped the video and you found these values one at a time by hand, by computing that average velocity, it's not difficult work, but it is quite tedious. Repeating the same calculations over and over again, just changing the values of the inputs. So there's lots of fantastic tools to automate such tedium. One of them is spreadsheets. I'm going to show you real quick. I'm going to switch over. I've got one ready. kind of give you an idea of how you could use a spreadsheet to take some of the tedium out of this, making such a table. I don't have a way to share it on a screen, but if you have a TI calculator and you want to ask me about it, I can give you some advice for how you can easily use a TI calculator to sort of automate some of these repetitious calculations. In your homework problems on the activity sheet and in the book that I'm going to ask you to look at, you're going to be asked to kind of find a bunch of these either tangent slopes or average velocities. And so if you want to, you can try to use one of these tools that I'm going to suggest to take the tedium out of that, okay? So what do we need to know? You're not going to be able to see it when we move over to the spreadsheet. So maybe if you wanted to jot it down, what you're going to have to remember is what this position function is, 4.9 times t squared. I'll remind you. And I think what I'm going to do when we switch over to the spreadsheet, let me switch colors here real quick so it's not so repetitious. I'm going to try to reproduce this first row. So you might want to write that number down too, 53.9 when we averaged over a time interval from 5 to 6 seconds, okay? So you maybe want to write down that row of the table that I just highlighted in pink there, together with what this S of t is. You can pause the video and write that down. I'm just going to make the switch right now. Switching over to, I said a spreadsheet. You can use any, there's lots of spreadsheets, right? Apple's Pages, Microsoft Excel, some of those things are free, some of them aren't free. Here I'm using Google Sheets. Google Sheets behaves a lot like Microsoft Excel, like a lot of spreadsheets, and it does happen to be free. So it's something that you don't have to make any purchase to use. I'm going to assume for purposes of this conversation that you're somewhat familiar with what a spreadsheet is, rows and columns, so I'm not going to try to start at basic tutorial level, but let me just show you how you could reproduce that table, maybe if you're comfortable using these spreadsheets, and I'll try to make this quick so the video doesn't get too long. So in this first column here, I'm going to put the number at the end of the time interval that I want to compute, 6. All right, so I'm thinking this is from time interval t equals 5 to t equals 6. And then in the second one, with an equal sign to make it a formula, I'm going to compute the average. So I'm going to be taking a fraction, the numerator and denominator, so I'm going to make some parentheses so that I get the order of operations right. And then I'm going to tell it, well, I want to take 4.9, I'm thinking of the S of t function, 4.9, and I want to multiply it by the value of the cell to the left. So I'm gonna put a parenthesis and then click this. I'm not gonna hard enter the 6 because I'm trying to get the spreadsheet to do things automatically for me. So I just click that, and you can see in Google Sheets, it's called the cell A1, and it made it a color. And I want to subtract 5 from that. Excuse me, no, I don't. I want to plug in that in. So I'm trying to calculate where the thing is when time is 6. So that A1 needs to get squared. And then I'm going to subtract from that 4.9 times 5 squared. Okay, so this is the difference in the position. It's the change in position. If I try to mouse over it, this is S of 6. So 4.9 times 6 squared minus S of 5, 4.9 times 5 squared. Okay, and then I need to divide that. By the change in the time. So again, I'm not going to use the number 6, but rather just click this because it's kind of my variable and subtract 5 from it. There's my change in time. And if I hit enter, it reproduces that number you wrote down, 53.9, and the units on it are meters per second. So the benefit of putting it in as a formula like that is I can now say things like, oh, if you want to do it, say, from to the interval that ends in 5.1 seconds, or 5.05 seconds, I think was one of them, or 5.01 seconds, or 5.001 seconds. Then if I click on the cell where I entered the formula, in the lower right-hand corner, you can see this little blue box. Click and hold it and drag down. It's going to update these cells using the values to the left. So that's how I can quickly reproduce that table. And if I want to, I can do it to arbitrary precision. If you want 3 zeros, if you want 4 zeros, again, you just always have to click on a cell. This is called copying the formula. You drag it down. So I can see that the closer and closer that we get this number to 5, that is the smaller and smaller time interval that we average over, the closer and closer the average velocity gets to 49. So that's more evidence that our guess was correct. This is 49 meters per second squared. Okay, so I'm going to come back to the whiteboard here real quick. We're going to wrap things up with what we've been talking about in this lecture, and then it'll be time for you to download the activity, work on that thing, and when you're done with it, you're going to look at the homework problems in the book, check your answers there on Slader, and hopefully come talk to me in one of our interactive Zoom meetings or my office hours where we can work on those homework problems together, talk about it. We can share some screens. But here, let me get done because I'm making this video too long. So what's the summary? What's the takeaway message that I want to send you with from watching this video? The summary is that the tangent line problem and the velocity problem, although they're very different in their origins, tangent line problem is a problem in geometry, analytic geometry. The velocity problem comes from physics. They have the same mathematical essence. These two problems were mathematically the same. And in particular, what do I mean by that? In both cases, we got interested in the value of some function. In the tangent line problem, the function was the secant slopes, thing that was giving us the secant slopes when we plugged in an x. In the velocity problem, the function was the average velocities, that s of t minus s of 5 over t minus 5. And we were interested in those functions precisely at an input that we couldn't use. We couldn't evaluate the secant slope function when x was 1. We couldn't evaluate the average velocity when t is 5. So in both problems, we were looking at a function, and we were interested in the value of that function at sort of a forbidden value of its, not in its domain. The secant slope function was defined for every x except 1, but 1 was right where I wanted to know what it was doing. The same for the average velocity function. I wanted to know its value at 5, but it's not defined at 5. So in both cases, what did we do? We looked at the outputs of those functions for inputs that got closer and closer to those forbidden values. Yeah. In the secant slope, we chose x closer and closer to 1 and kind of wrote down a table. For the average velocity, we chose t closer and closer to 5. We wrote down a table. And it gave us a guess for what this sort of forbidden value should be. All right, so that mathematical idea is called a limit. We were taking the limit of that secant slope function of those average velocity functions. And limit, quite literally, is the subject of chapter 2 in this book. So hopefully this tangent and velocity problems motivated you to study limits with me, and also gives you some appreciation for the power of mathematics, that often the case, different problems and applications kind of have the same mathematical essence. And it's one of the things that mathematics can give you a tool to be powerful about. Okay, so thank you for listening.